Well, we've looked at the simple OpenMP notes, and those are to get you started, get you going on Project Zero and so on. But let's do a deeper dive into OpenMP, like the things you'll know for the other OpenMP projects. So here we go. OpenMP stands for Open Multi-Processing. It's a multi-vendor standard, so it's not like one vendor picked this up and maybe a couple more adopted it. This is widespread across the industry. One of the interesting things about it is it's largely compiler directive, meaning you put little marks in your code and the compiler fills in the parallelism. That's kind of cool. And for the most part, it doesn't take that long to inject these marks into your code. Okay. It's also library based. There's a library that gets linked in as well, and you'll see how to do this. The threads that OpenMP creates share a single executable. Okay. So it's one compiled code that they all the cores are going to share. So it's not like even the executable gets transmitted to each core. It doesn't. It's somewhere in memory, and all the cores know to go there and execute it. But each core is going to have, or each thread is going to have its own state, okay? Its own registers, its own program counter, and its own stack pointer. But they're executing the same code. Typically, OpenMP doesn't require very dramatic code changes in your code. That's one of the greatest things. And I think OpenMP probably gives you the biggest multi-thread benefit per the amount of work that you have to put into it. Okay. Yeah, there may be ways of getting more benefit, but per the amount of work you put in to make your code compatible, nah, I think this is pretty good. Who's in the OpenMP consortium? Round up the usual suspects. There's AMD and ARM, Cray, Fujitsu, Hewlett Packard, Intel, IBM. Again, this is very widespread across the industry. And of course, we also have, well, things like NASA, some of the government labs, and so on. Okay, here's what it isn't. It doesn't check for data dependencies, conflicts, deadlocks, race conditions. You're responsible for avoiding those on your own. And this is why I like to say programming parallel is really not that hard. It's programming it well that's the hard part. And of course, that's your value added. I could get a high school student to inject those directives into the code, but it's knowing the things to look out for or how to make it run better. That is your value added. Okay. Doesn't check for non-conforming code sequences. We'll talk about what that means. There are certain formats that, for instance, the for loops have to take. OpenMP does not guarantee identical behavior across vendors or across different hardware or even on the same hardware. Every time you run your OpenMP code, the scheduler is going to schedule the threads differently. It just is. Now, a lot of times we don't care, but again, this is part of your value added is to know that and know that know what to do about it. OpenMP does not guarantee the order in which the threads execute. This is part of the non-determinism of the scheduler. It's not overhead free. There's a certain amount of overhead to firing up these threads, which says, if you've got a tiny amount of data, don't multi-thread it. The overhead will dominate what execution you get. And this will become important when we get to the caching notes. OpenMP does not prevent you from writing code that triggers performance problems because of the cache. It's something called false sharing, and we'll get to it in the cache notes. But what you'll see is OpenMP does not prevent it, and in fact, it makes it really easy to do. Again, part of your value added. Okay, you're going to know what false sharing's about. You're going to know how to avoid it. Okay, in a multi-threaded program, you typically have this. In a single thread program, you typically have this. But notice the heap is common to all the threads. The globals are common to all the threads. All the threads are executing the same executable. It's the stacks that are different. Each thread needs its own stack because it's going to assign its own local variables, its own function arguments, and so on. Okay, for using OpenMP on Linux, you do everything exactly the same except you add this -f OpenMP. Okay, using OpenMP in Visual Studio, you go to the project menu, go to project properties, and then if you look for configuration properties, C/C++ language, OpenMP support, it probably says no. Click on it and change it to yes. Okay, that's it. Every so often you will get this ridiculous cryptic error using OpenMP. And I have no idea what it is, but here's what you do about it. Hopefully you never encounter it. Okay. To see if OpenMP is supported on your system, it's important to do this like right at the top, like main, left curly brace, and now this. There's a If you've got OpenMP turned on, and your system supports it, there is an automatic defined constant called underbar, all caps, OpenMP defined. And so we're saying, well, if that's defined, well, that tells us what's supported. And in fact, that is not just defined, it's the release number. Okay. But if that's not defined, that means OpenMP is not supported. And what that probably means is you didn't turn it on. If you're on Linux, do this. If you're on Visual Studio, do that. If you didn't turn it on, then um, yeah, it'll say this. Typically, it's supported everywhere these days. But anyway, do this. Um, if you print that out, it doesn't give you a version number. It gives you a year and a month. Well, here's the conversion table. Here are the years and the months, and here are the version numbers that correspond to that year and month. So Flip by default, uses G++ 11.4, which if you do this, you can find out that's OpenMP version 4.5, which is pretty good. The most recent G++ also uses that. Visual Studio, for some reason, seems to be locked at OMP 2.0. Now, for what we're doing, won't matter. We're using the real fundamental parts of OpenMP, not some of the exotic things. But someday you might care. Okay, here are some of the library calls. Set the number of threads. Okay, next time I ask for threads, how many should I create? 4, maybe. Get the number of processors. This is really getting the number of cores. Although if you're in hyper-threading mode, and we'll talk about what that means later, um, it's the number of hyper-threads, not the number of physical cores. That's kind of annoying. Setting the number of available threads to the number of cores, well, you can just ask the number of cores and set the threads to that. Asking how many threads this program's using now there's a set num threads, here's a get num threads. And asking which thread number the code running on this thread is, you can do that. So there are some nice library functions. You will especially see in the examples, will you use this one? Okay, so I'm gonna let's say I'm going to call this with 4. Now that doesn't make 4 threads. What that does is say, next time I'm asking for threads, give me 4. So here's what happens. Pragma, pound pragma, OMP, is what you inject into your program. That's a flag to the compiler to generate some OpenMP code. And this is one of the great things about OpenMP is you don't have to actually make your own threads and all of that and all the drama and difficulty that comes with that, but you just say, I want it. So pragma OMP parallel. At that moment, it creates however many threads you've asked for. Okay? So think of it this way. Along comes your single threaded program, and you say pragma OMP parallel, and suddenly one horse becomes four horses. Apologies to Ben Hur. Okay? One other thing you need to print out or you need to include OMP.h because you've turned on OpenMP with that -f OpenMP or with the Visual Studio, you don't have to specify where in the world that is, it will know. So here we go. So here's a program I created, OMP set num threads. Let's use 8. That doesn't make 8. It just says next time I ask, make 8. But here I'm asking, pragma OMP parallel, and all 8 threads are executing this line of code. Okay, hello world from thread number. I ran this several times in a row, and here's what I got. They all ran. They all did the correct thing, but notice the order. There is never the same order to any of this. Not even the same who went first, who went last. There is never a guarantee of thread execution order in an OpenMP program. Okay, we just have to deal with that. Now, there's some exotic ways you can synchronize this, but by and large, that slows everything down. Because what that means is if you do that, that means one thread has to come to a grinding halt, waiting for the next thread to go around it. That sort of destroys the reason to have parallelism in the first place. So, yeah, there is no guarantee of thread execution order. So I've broken this up into 3 parts. That's the end of part 1. So come join me for part 2. The story just gets better and better.